This is a simulation of a vapor-liquid equilibrium measurement apparatus. On the right side of the screen, you can see a diagram of this apparatus. In the boiling flask here, there is 100 milliliters of a binary mixture consisting of liquid A and liquid B. There is a heating element that boils the liquid, which evaporates and goes up this tube, down this tube, and then goes up into the complete condenser. The condensed liquid runs down and enters into this collection chamber, which has a valve to collect distillate. The liquid distillate in the collection chamber has the same composition as the vapor leaving the boiling chamber because the condenser is a complete condenser. Note that the condenser is open to the atmosphere at the top in order to maintain a system pressure of 1 atmosphere. The distillate liquid then runs back down this tube and is recirculated back into the boiling chamber. Because the liquid re-enters the boiling chamber, the system is equivalent to a flash batch distillation column running at total reflux. In the real world, one would allow this system to run for an extended period of time in order to let the system come to equilibrium before making measurements. That is one benefit of this virtual lab. One does not have to wait for minutes or hours in order to take a new measurement with different conditions. Inside the boiling flask is 100 milliliters of liquid. Currently, there is 50 milliliters of component A and 50 milliliters of component B, as we can see under where it says boiling flask conditions. We can adjust the volume of component A. Let's set it to 20 milliliters by moving this slider at the top of the screen. And now the boiling flask contains 20 milliliters of component A and 80 milliliters of component B. In order to make measurements, you must first determine the liquid compositions you want to take measurements for. I'm going to take 3 measurements, one with 20 milliliters of component A, one with 50 milliliters of component A, and one with 80 milliliters of component A. So, since there is already 20 milliliters of component A in the flask, I'm just going to click Collect Sample. You can see the test tube filling up with liquid on the right side of the screen here, and then the test tube of liquid is put through a chromatograph, and we find that the vapor composition is displayed on the bottom left here. Let's change the slider to 50 milliliters of component A and take our next measurement. Now finally, let's change the slider to 80 milliliters of component A and take our final measurement. As you can see, the volumes of component A and B, shown in blue here, have decreased. These values cannot go below 0, so you cannot put 50 milliliters of component A in the boiling flask if there's only 40 milliliters of component A remaining in your inventory. You're going to want to take more than 3 measurements, but for the purpose of this video, let's assume I've taken as many measurements as I will need. To access your data, click Download Measurements here above the canvas. This will provide you with a spreadsheet containing all the relevant information for your lab. I'll pull this spreadsheet up now. As you can see, the spreadsheet is completely unformatted, so I'm going to click over to a spreadsheet that I have done some formatting to make it look a bit nicer. Here is our data. As you can see, the spreadsheet contains the molecular weights, densities, and Antoine constants for components A and B. You will need these to determine the Margoule's constants. Down at the bottom, we have a list of all 3 of our measurements. I'm now going to pull up an example spreadsheet in which we can determine the Margoule's equation parameters. Here is a list of the measurements taken by this individual, and above it is the molecular weights, densities, and Antoine constants that this person had in their virtual lab. First, they determine the molar densities of each component, which are listed here. Next, we use the molar densities and volumes of components A and B to calculate the liquid composition for each data point. If you need help finding the formula to determine liquid composition, just go to the Equations tab in the Virtual Laboratory documentation. See here, equation 8 is the one we're looking for. After determining liquid mole fraction for each data point, we have 20 liquid mole fractions and the corresponding 20 vapor mole fractions. That means we can make an equilibrium plot, which is shown here below. Just ignore the line going through the data points. We'll get to that in a couple minutes. After determining liquid mole fractions, we need to find the saturation pressures of each component for their given temperatures. We can use Antoine's equation and the Antoine equation constants listed up here to find the saturation pressures of components A and B for the temperatures listed in column E here. Finally, we will set arbitrary values for the Margoul's equation parameters. I'll set them both to 0.5 for now, and we'll use the Margoul's equation to calculate the activity coefficients for components A and B at each data point. We can use the activity coefficient to calculate the theoretical vapor mole fractions of components A and B, and then find the difference between the theoretical vapor mole fractions and the measured vapor mole fractions, which we call the error. Down here is the sum squared of the errors, which we will want to minimize. Next, we will use Excel Solver to change the Margoul's parameters to values which will minimize the sum squared of the error. So now I'll go into Excel Solver and set the objective to the sum squared of the error, which is cell T44. And we'll make Solver find a minimum value by changing cells N7 and O7. Finally, we want to constrain the Margoul's parameters to a value between -2 and +2, so I'll set some constraints here. Finally, we click Solve, and it will minimize the sum squared error by altering the Margoul's parameters. Solver found a value for A12 of 0.68 and a value for A21 of 0.30. The correct parameters are listed below, with A12 actually being 0.65 and A21 actually being 0.35. These are the correct answers. So we were pretty close, especially considering that Margoul's parameters can be anywhere between -2 and +2. Finally, we will want to determine the 95% confidence limits, which we recommend using a graphical method to do. For information on how to determine the 95% confidence interval limits, view the screencast under the Analyzing Data section of the documentation for the virtual lab. Now, let's return to this equilibrium plot. The line passing through these data points is calculated using the Margoul's parameters we just solved for. And as you can see, it matches the data pretty well. Now, returning to the virtual lab, we can submit our answers and view the correct Margoul's parameters by clicking Submit Answers near the top of the page here. Enter the value for A12 and A21 in the boxes on the left, and then enter the lower and upper confidence intervals to the right. Our A12 value is 0.68 with confidence limits between 0.51 and 0.81, so I'll enter those now. And the A21 value is 0.30 with confidence limits between 0.19 and 0.41, so I'll enter those now. Finally, I'll write the names of myself and my partner, John Falconer, and press View Results. As you can see, our estimate is on the left and the correct Margoul's constants are on the right. The correct Margoul's constant falls between our confidence limits, so it looks like we did a pretty good job. If you want to try the lab over again with different Margoul's constants and liquid properties, press the Reset Laboratory button to start again. Otherwise, if you're happy with your result, send a screenshot of this page to your instructor along with your Excel spreadsheet and lab report. Thanks for watching.